All right, so let's check out the practice homework. And they get a blue box here. The blue box is just kind of a practice problem to help you practice exactly this problem. I'm just going to write to the question here, which is the white part here in the bottom right. And they do have a picture, but the picture I think is a little overly complicated. Here's my box. There's a tension to the right. Everything that has mass will experience gravity. Gravity is straight down. And there's surface contact. So surface contact means there's a normal force perpendicular with the surface. Here's our picture. Compared to their picture over here, it just looks a little bit more busy than it needs to be. Here's a nice straight picture. And then what we would do next here is we would sum the forces. Now, if we look in the x direction, there's only one force pointing to the right, and that's tension. And Newton says when you sum the forces, that equals ma. That is the acceleration in the x direction. And then if we look at the forces in the y direction, so we'll sum the forces in the y direction. We've got the normal force that's up. We've got force of gravity down. Newton says this equals ma. That's the acceleration in the y direction. But the box isn't moving up or down. So when the box travels along the table, the box isn't going up or down and passing through the table. The box is just sliding nicely, which means its acceleration in the y direction is 0. And this is an assumption you do have to make a lot, even though the problem may not say it. It does say that there's a horizontal force is about as close as we're going to get, and a frictionless surface. So there's no bumping up or down. The box isn't going into the air. It's not falling through the world. There's no acceleration in the y direction. And this is a common assumption that you do have to make for these problems. It won't directly state it. But when you're pulling an object, it's just moving in the x direction. So that means at least for the y direction, we get the normal force. The normal force is equal to the weight of gravity. But something I want to say really quick, summing the forces, what this is technically doing is it's generating math equations for us to solve things. So that's the point of drawing this picture. The picture is meant to help your brain do the math. Once you have your picture, you can then generate the math equations from Newton's second law. You add all the forces together in the x direction, that equals ma. Add all the forces together in the y direction, that'll also equal ma, but for the y direction. And then that generates equations for us to solve. So in this particular one, they want us to know the acceleration. Well, we know tension equals mass times acceleration. That's the equation we just generated from summing the forces in the x direction. And they're telling us, now this is what can be a little confusing sometimes with Pearson, because the picture says 20 newtons, but if you go to the problem, it actually says the person is pulling with 30 newtons. So they're telling us the tension is actually 30 newtons, newtons being the unit of force. And so it's something to be careful about. The picture does say 20, but the actual problem here says to use 30. So try to make sure you're checking that out. And they also need to tell us, now this is what's goofy, is because we're going to actually go to the picture for the mass. So they say in the picture the mass is 40 because we do need the mass to solve this. So they're saying the tension is 30 in the problem. The picture says the mass is 40, which means we can solve for acceleration then. 30 divided by 40, which is 3/4, which is 0.75. And that's our acceleration. I do have my calculator working today. Oh, they want the velocity though. Okay, so we need to keep going. They actually want a velocity here. So this is what I said at the starting. That, I already moved that paper away. But what I said at the starting is we started class with these kinematic variables. And we started class with these kinematic variables and the kinematic equations. Now what we're going to do is solve for acceleration by summing the forces. And once we have acceleration, we can then use the kinematic equations. And that's what this problem is having us do, is now that we've solved the acceleration from summing the forces, They're also telling us the box is going to travel a distance of 0.3 meters, and it's starting from rest, so our initial velocity is 0. Here's the 3 pieces of information that, remember, we need 3 pieces in order to start solving the kinematics, and there we are. And they want us to figure out velocity, so the equation you'll want to use is this one. That's final velocity squared, initial squared, plus 2ax is the equation we want to use. We're looking for final velocity. We know the initial is 0. We know the acceleration is 3/4. We just figured it out from summing the forces. And they're telling us our y displacement is 0.3. So we're just going to take the square root of that number, and I do have my batteries in my calculator this time, so let's see. Just doing a quick 2 times 3/4 will be 3/2 times 0.3. So that's what I'm going to type in. And, I guess, whoops. Try that again. 3/2 times 0.3 is 0.45. And that's my answer. Oh, whoops. And I had to take the square root. So this is velocity squared. So I typed this into my calculator. I still need to take the square root of that, though. So I was going to do that. Square root of 0.45 is 0.67. So let's go down here. And 0.67 is my answer there. And that's the question for number 1. Check out the second one. A box rests on a frozen pond. All right, there's my frozen pond. There's my box. Notice the same picture I draw a lot for all these different things. There's no reason to make it more complicated than it needs to be. What they're ultimately trying to say is we have a nice flat surface with some flat object on it. That's what they're ultimately trying to say. So what if it's a box in a pond? Whatever. There's my picture. A fisherman applies a force. So here's a human being coming in to apply a force. This is the applied force. Remember, one of the 5. Oops, I clicked that. And so here's where I would start drawing that in. So a fisherman is applying a force. So there's our force applied. Now the box has mass. So that means there's a force of gravity. There's contact with this surface. And there's always a normal force that's perpendicular with the surface. So there we go. Now the problem does say it's frictionless. So I'm not going to put any friction to the left because they're telling us it's frictionless. So here's all the forces, the 5 forces. Here they all are. So force applied is 1, gravity is 2, the normal force is 3. The tension is a 4th force, but there's no rope here, so there's no tension. And then the 5th one is friction, but they're telling us there's no friction. So we only have 3 of the 5 forces. And that's all we're going to concern ourselves with. And then we'll go ahead and we'll sum the forces in the x direction. We're going to add up all the forces in the x direction. And there's only the force applied. That's it. And Newton says once you've added all the forces in the x direction, that'll equal mass times acceleration in the x direction. And then we'll look at the forces in the y direction. We'll see that there's the normal force up. The force of gravity is down, so that's going to get a minus sign. And Newton says, whenever you sum the forces, that will equal mass times acceleration. In this case, we're talking about the y direction, so that's why I put a subscript y here. And again, here is the common assumption. Notice it's not stated anywhere in the problem. This box is going to be pushed evenly across the surface. The box is not going to jump into the air. It's not going to fall through the pond. It's not going to jump back up. It's going to go across smoothly, which means there's no acceleration in the y direction. It's not moving up or down. And this is an assumption that you have to make a lot. I say assumption because the problem doesn't state it. But this is what it means right now. Like, just to say this again. When I push my pen, there's my actual desk. When I push my pen on the desk, I'm pushing my pen isn't falling through my desk. It's not jumping off the desk. The acceleration in the y direction is 0 when you push things along a surface. And so that's the math we have to connect to, is that the acceleration in the y direction is 0, and then that tells us that the normal force equals the force of gravity. And again, these two equations are generating math for us. That's the point of summing the forces, to generate a piece of math so you can then solve the problem. And we're concerned again with this first one, that the force applied equals mass times acceleration is what we got from our first equation. And they're telling us the force applied is 51 newtons. So I'm just reading the problem. It says the fisherman applies a force of 51 newtons. And it says this produces an acceleration of 2.5. And so there we go. Here's my result. And then I can solve for mass, which is what they want. So 51 divided by 2.15. So mass is 51 divided by 2.5. And then that's what I'll punch into my calculator. And that is 20.4. And let me just check the units of kilograms so I don't get burned like last homework where they changed the units on me. And that stops. I mentioned that in class. I'm pretty sure that Pearson for the first couple of weeks will mix up the units for us, but then they'll stop doing that. Everything will just be in proper units, which is how I'd prefer it. And so our answer there is 20.4. And there is that one. So now we got a 61 kilogram skater. So your average adult is 70 kilograms. Your average adult is about 70 kilograms in mass, just to give you an idea. So 61 kilograms is about the mass of an average adult. And they're telling us the mass. And that might be something you want to write down just to know that that's a number that's been given. Is moving initially. So that's an initial velocity. That's one of the kinematic variables. 3.45 is given in proper units, so that's awesome. Now they say a rough horizontal surface. When they say rough, that implies friction then. And they're going to come to rest in 3.8 seconds. So there's another value they gave us there. Remember, coming to rest means final velocity 0. They're coming to rest. So the skater skating along on their round skates, and they have some initial velocity, and then they skate, and then they stop. And then they're stopped. Final velocity 0. Now during this course, friction stopped them. And we can figure out what that acceleration is by using one of the kinematic equations. Specifically this one. We know the final velocity is 0. We're trying to get the acceleration. We know the time is 3.8. And we know the initial velocity was 3.45. And so we can solve for acceleration. We'll move this to the left side. And then we'll divide by 3.8. And that is our acceleration. Notice it's negative because acceleration will point in the negative direction here because it's trying to slow the person down. So I'm going to type in my calculator 3.45 divided by 3.8. And that is a negative 0.91. So I'm going to round that to a 1. And that's the acceleration. That's her acceleration. The acceleration due to friction, which is slowing the skater down. Now, we also know that the sum of forces equals mass times acceleration. And we know her mass, it's 61 kilograms. We just figured out the acceleration. We just figured it out. There it is. And so this must be then the force from friction. So let me draw this really fast. Here's the skater. The skater's a box and a flat surface. The skater has a gravity down because they have mass. They're in contact with the ice, so there's a normal force. Now there's no force pushing on the skater. The skater's moving to the right, which means the only force here is the force of friction in the x direction. So when we sum our forces in the x direction, we have just force of friction pointing to the left. And then that's what Newton says equals ma. And so that's what we end up solving for here. We're solving for the force of friction. And so that's what I'll do. The force of friction is 61 times 0.91. We'll check for a moment if they want the minus sign. So 61, actually I'm going to use my non-rounded value here. So take that times 61, and I get a force, my sum of forces here being 55.4, I'll round that. So to one decimal place, 55.4 newtons. Now, technically, the force of friction is pointing to the left. Oops, here's my picture. The force of friction is pointing to the left, which means technically it has a minus sign. But the acceleration also has a minus sign in here. So let's see. It just says what force. It doesn't say whether I should use magnitude or sign, but the force of friction is technically to the left, which means it should technically have a minus sign. Let's see what happens. So I'm going to put in minus 55.4, and let's see what happens. And it doesn't like that. So there's nothing here to tell me what the mistake is. So, well, it does say check your signs. Now, if you're a student, when you see check your signs, are you confident that means you have the right answer, just the wrong sign? Are you confident of that? Because that's what it means. If the computer says check your signs, it means you have the right answer, just the wrong sign. So I'm not going to nitpick over that. It should be technically minus 55.4 because it is technically to the left. And it doesn't say anywhere to ask for magnitude or anything. But same deal with the test. You know, if we're in a testing situation and you got 55.4 and you wrote negative down, well, look, to get 55.4 means you did all of this correct. And that's what's important to me. To get this number means you did all of this correct. And so the minus sign, or without having a minus sign, that look, you've gone almost the entire way perfectly if you get this number. So it should technically be minus, but in a testing situation, I would just write the minus sign in and not dock you any credit for it. I give you full credit because getting that number is the hardest part there. So let's check out the next one. We have another block sitting on a table. So you notice, guess what picture I'm going to draw? I'm going to draw a flat surface with a square on it. And I'm telling you, this picture goes a long way. So we have a block, 9 kilograms. It's on a frictionless table, so there's no friction this time. And there's a force applied to it and a horizontal force. So there's a horizontal force being applied, so that's our applied force. Now, we have the force of gravity down. There's surface contact, so there's a normal force up. They're telling us there's no friction, so there's no friction to the left. That's the fourth force. The fifth force is tension, but there's no rope here, so that's all the forces. We're done. So we'll now do the math setup. We'll sum the forces in the x direction. There's only one. That's force applied. Newton says when you sum all the forces, that equals ma. We'll do the same thing in the y direction. We have the normal force up, force of gravity down. Newton says this equals ma in the y direction, but we know that the acceleration is 0 in the y direction because the box isn't bouncing up and down. It's just traveling smoothly. And so from the second equation, we get that the normal force equals Fg. the force of gravity. Remember, the force of gravity is m times g. So just like the previous problems, the parts that's probably going to be of interest to us is in this first equation here. And part A says, what is the acceleration of the block? Okay, well, we know the force applied is 14 newtons from the problem. We know the mass of the block is 9. And so let me just write this in case it's not clear. This is what we're doing. We found from equation 1, force applied equals mass times acceleration in the x direction. The force applied is 14. The mass of the block is 9. And so we can solve for the acceleration. The acceleration will be 14 over 9. And that's what I'll plug into my calculator. 14 divided by 9 is, I just put in new batteries, so it's not giving me decimal. What is that? I'm in pretty print or something. Oh no, I'm in exact. Here we go. I want that to be approximate. There we go. 14.9 is 1.56. And that's what I'll put in for my answer for the acceleration. And part B, what is the speed of the block after it has moved 0.5 meters? So we have the acceleration, we have the displacement, they're telling us it's 0.5 meters, and does it say it anywhere? It does. So we're looking, remember, when it comes to the kinematic variables, we need 3 pieces of information. We have 2. So we have to go looking for one more piece of information. And the other piece I'm looking for is right here, this word, or these words, sits at rest. Sits at rest means its initial velocity is 0. There's our third piece of information to use the kinematic equations. So they want to know what is the speed after distance. So they're asking what is the final velocity is what they're asking for. And the equation, the kinematic equation to use there is then this one. So we're looking for the final velocity. We know the initial is 0 because it starts from rest. We figured out the acceleration is 14/9, and it's moving a displacement of 0.5, which is a half. And the reason I wrote as a half is because 2 times a half will cancel each other out. So the final velocity is the square root of 14 over 9. That's what I'm going to type into my calculator. Square root of 14 divided by 9 is 1.25. And that's my answer. Let's go down there, type that in. And there is part B. Very good, straightforward problem. Summing the forces to get the acceleration, and then using the kinematic equations to figure out another piece of information. So we got here, got some blocks being pulled. Now the blocks being pulled is a problem I like a lot because it really tests your understanding about some things here. So before I look at these questions, let me just say this. We got these blocks being pulled. I was going to make the bigger one. I'm just going to make this one bigger. I'm going to call this 10 kilograms, and I'll call this 5 kilograms. And let's say the acceleration of this system is 2 meters per second squared. So first off, both of these blocks must have the same acceleration. Because if they don't, then the rope stretches. And our ropes don't stretch. Our ropes are magical. They only transmit force. So both of these blocks must have the same acceleration. Otherwise, they're getting farther apart from each other or they'd be coming together. So to travel the same distance apart means they must have the same acceleration. Now, notice what the forces are, though. Because force equals ma. Well, if this block is 10 kilograms with an acceleration of 2, So 10 kilograms with an acceleration of 2 means this block is experiencing 20 newtons of force. While this block, F equals ma, well, this block is 5 kilograms, but it's still experiencing 2 meters per second acceleration, which means that it has 10 newtons of force. It has half the amount of force than the bigger block does. So this force, the 20 newtons and the 10 newtons, this force must come from the person pulling on the blocks. So this person must be pulling with 30 newtons of force. They must be, because 20 newtons goes into moving the 10 kilogram block and another 10 newtons goes into moving the 5 kilogram block. So we have a total of 30 newtons to move these two blocks, which means this person must be pulling with 30 newtons. This also means the tension in this rope must be 30 newtons because this rope is pulling both of these blocks. But this rope is only pulling this block, and that block only needs 10 newtons, which means the tension in this rope is only 10 newtons because it just needs to pull 10. And assigning these numbers is what can be is what makes this a good problem to understand. I guess my point I'm trying to make here is a common example is people think these ropes have the same tensions. In other words, they'll think, well, if this rope is 30 newtons, this one must be too. But it can't be because this rope is pulling a smaller block. So it can't be the same amount. And that's most likely what the stuff they're going to be asking here is. So if we look at part A, it says, which of the following statements correctly describes a relationship between the accelerations? So this is how I started out. These blocks must have the same acceleration. If they do not, then these blocks are either getting closer together or they're moving farther apart. And let me just see if I can get another pen here. So here we go. I got 2 pens. If they have the same acceleration, then they stay equal with each other if they have the same acceleration. Now, if this one is moving faster, well, then it goes farther away from it because it's accelerating. If this one is moving faster, then it'll collide with this one. So for order for blocks to stay the same distance from each other as you're pulling them means they must have the same acceleration. And so these blocks, that's the first question. They must have the same acceleration, which is this third one here. Both blocks have the same acceleration. Because if they were different, then the blocks would no longer stay next to each other like this. They would either separate or get closer together if their accelerations were different. So part B, almost certainly about the tension, because these are just good standard questions for this type of problem. This is a good problem. I always have a test question that has 2 blocks being pulled that has this type of stuff in it. So part B says, how does the magnitudes of the tensions compare? Well, that's what I talked about earlier. The tension in this first rope must be larger than the tension in the second rope because the first rope pulls the entire system. This first rope pulls the entire system, while the second rope only pulls the last block. So the first rope pulls everything, while the second rope only pulls the last block. The tension in the first rope must be greater because it's pulling more. And now they're calling the first rope, if we look at the picture, we're calling it string 1. So this is tension 1. Tension 1, the first selection, tension 1 must be greater than tension 2 because tension 1 is pulling more stuff. It's simply pulling more stuff. And so that would have to be our answer there. And now I don't do multiple choice questions for the test. Usually I have you figure out some number here. But this is a very good type of test question. Pulling 2 blocks with ropes, just because it really tests some ideas to see if you're understanding. So very good question there. Let's check out number 6. What is the mass of a book that weighs that? So weight, remember, is the force of gravity, and that's simply given by mg. And they're telling us the weight is that a 6 or an 8? That's a 3.6. They're telling us the weight is 3.6. The acceleration due to gravity is 9.8. And so we can just solve for the mass. 3.6 divided by 9.8 is the mass. That's what I'll type in, 3.6 divided by 9.8 to get a mass of 0.3. I'll round the second digit to a 7, 0.37. There is my answer. I should have tried a G of 10 there. I'm just curious. So in the same land, what is the weight of the dog whose mass is that? I'm going to try a value of 10 for G here, just out of curiosity. Now, the same deal with the second one. Weight is mg. Remember, weight is the force of gravity. It's two names for the same thing. Now they want to know, what is the weight of a dog that has a mass of 28? It has a mass of 28. So now we're going to figure out, and G, I'm going to call G 10, just out of curiosity, because sometimes this book does use G as 10. I'm just curious what the computer grading will say. So 28 times 10 is 280. So 280 newtons. So what happens if I use 280? Let's see what the correct answer is. 28 times 9.8. The correct answer with 9.8 is 274.4. So a pretty big difference between 9.8 and 10. Let's see what it says for the 280. What do you think about that? And it takes it. So, and notice it rounded it down to 275, which is this answer here. So, just my experience that this book does take G as 10. Not something I would push too hard, though, meaning that I think you're pushing your luck if you use 10, because G is technically 9.8. And the larger your mass is, the more error this number will have. So, stick with 9.8. It's the safer value. But there was a quick check. They do accept G as 10. But I do consider that to be a little risky if you choose to do that. And let's check out this last one. A standard bathroom scale. All right. So the scale is always a fun one. So now, notice my picture. It's another box on a surface. But now what I'm going to do is I'm going to put a person standing on the box. So my picture's slightly different this time. Obviously, the box is the scale now. But the scale actually reads the normal force. So the scale doesn't actually read your weight. It reads the normal force. So if you think about the person here, so here's the person. The person has a force of gravity down, and they have a normal force up. The normal force coming from the scale because they're standing on the scale. Now, if we sum the forces in the x direction, there aren't any because there's nothing left or right. So Newton says this equals ma. Well, we can see then A must be 0 then because the mass isn't. And if we look at the y direction, we have the normal going up, we have the force of gravity going down, and Newton says this equals ma. Now, in all the other examples, we've set A to 0 because our box has been sliding left or right. There's been no motion up or down. So we set A equals 0. Now it's just the opposite. Now our motion is up and down. There's no motion to the left or the right. So this is our equation now. We have the normal force. Now the force of gravity is mg. And then we have mass times acceleration. So now the equation we're getting is actually from the second one. And what the scale reads is the normal force. So I'm just going to solve for the normal force here by moving this to the other side. These actually have a factor of m in common. And so we can just factor that out. And here is actually what the scale reads. So if you're standing in your bathroom, now the chances are your bathroom's not moving. So if your entire bathroom is not moving, then the acceleration is 0. And if the acceleration is 0, then this equals mg, which is your weight. So you want to stand on a bathroom scale when the scale's not accelerating. That's when it gives your weight. But what if the scale is in an elevator that moves up or down? Well, if it moves up or down, that means there's an acceleration. And notice, if acceleration is positive, then the normal force, the reading on a scale, will increase. So the scale will say you weigh more. And that's from the acceleration of the elevator. Notice also that if you're dropping down the elevator, so now the elevator is going down. The elevator is going down. Notice if the acceleration is equal to g, then this is 0. And then the scale will read 0. So this is something I just got to say this really fast. I don't know if all astronauts go through this. I don't even know if any of them do. I'm sure some do. But there's this thing that's called the Vomit Comet. And it's a plane, Vomit Comet. It's a plane. And it's a plane where they do exactly this. So the plane will go way up into the air, the plane. And then it'll take now it goes as high as it can, and then it'll take a dive. And it purposely takes a dive such that the acceleration is equal to minus g. They purposely do that. The plane will come down with an acceleration of minus g, because at that point, you then start to feel weightless in the plane. You start to feel weightless in the plane. Because now the plane is falling at the same acceleration due to gravity, and then this is a way to simulate weightlessness for astronauts to do some testing in. Now, I think it only lasts maybe a minute or a minute and a half, so they go up, and then they have their weightlessness right here. This is where they're in free fall, and they feel weightless. And then they have to climb back up again, and then they have their free fall again. And I think this only lasts about like 90 seconds, and then they have to go up again. They can fall for 90 seconds. And it's called the Vomit Comet. And that's where they do testing for the feeling of weightlessness, so you can experience it before you actually have to go in space and try to work in it. So I don't know if all the astronauts go through that, but that's what we're dealing with, something similar here. So here's our ultimate equation for the scale. Here it is. If the acceleration is positive, the scale will read a larger number. If the acceleration is negative, then the normal force will go to 0. So let's look at the information we have. We have a 39 kilogram buoy. So we have the normal force equals 39, because they're telling us the mass. And the elevator begins to accelerate upwards. So up means positive at 0.4. So the acceleration is positive 0.4. And the acceleration due to gravity is 9.8. Now we have to be a little bit careful here. So I've tried to always state g is 9.8 and not without the minus sign, because the minus sign already got included right here. So when I said the force of gravity was down, I said the force of gravity is down right here. I then indicated that mathematically with this minus sign. So I can't, so here's the minus sign again. I've already included the minus sign. So if I say g is negative 9.8, that means I'm including another minus sign, which would make it positive then. So don't over-include minus signs. Once you include the direction, once you say the direction is down, that is the minus sign, and g is positive here. So this is n minus the mass. The mass is 39, and then g is 9.8. Right there, and the minus sign is already included. So just to be clear, if you're asking why I didn't put a minus sign on 9.8, because I already included the minus sign when I did my sum of forces. So again, g is 9.8. positive. That's what G is. It's a positive 9.8. There is G again, positive 9.8. These accelerations are going to be adding together, and then I'll get my normal force. So I'm going to do that. 9.8 and 0.4 is 10.2. So I have 10.2 times 39 to get 397.8 and newtons. So that's how much this boy will weigh. 300, and I'm just going to call that 398. 398 newtons. And there's our answer. And let me just say this again. If the acceleration was minus g, meaning the elevator was going down at the acceleration, that's when we would get this. We would get minus g plus g, which is 0, and then we'd get the normal force of 0. That's free fall. That's what the vomit comet is, where you can't touch the surface anymore because the surface is falling at the same rate of gravity. And so you get an experience of weightlessness. So there is the homework. I'll talk to you in class.